Okay, so for the particle model of EMR, we're looking at a new scientist named Planck. He suggested that there's a minimum amount of energy that electromagnetic radiation with a particular frequency can be used to transfer to matter. So what we're looking at is a very small individual piece of energies, otherwise known as a quantum. And as we get further along, you'll see that we also call it a photon. And it's a packet of energy. And this supports the duality portion of wave-particle theory because it's packets of energy that are moving along in the wave motion. So here the analogy is that Planck's theory is compared to a digital picture. The digital photo looks like one big piece, but actually if you were to zoom in on this video, you would see each one of these pixels. And each one of those pixels represents a photon or a packet of energy. So here Einstein is actually the one that came up with photons. So Planck came up with a quantum and Einstein came up with photon. And photon is the word that we use today, but the word quantum is what we use to talk about quantum physics. So Planck actually found a really simple formula that calculates the amount of energy, this little packet of energy, based on the frequency. And so energy of the particle, or energy of the electromagnetic radiation, is equal to h, which is a constant that he discovered, and frequency, or this energy can also be equal to Planck's constant times the speed of light in a vacuum over the wavelength of the electromagnetic radiation. And so this formula right here is the amount of energy for one single piece of quantum. If you had more than one photons, you need to look at the number of photons. So energy is equal to the number of photons times Planck's constant times the frequency. So here the E total, the total energy of the system, is equal to the number of photons times their individual energy. And so here's the link. The photons still linked to wave particles, so the new theory was beginning to develop that EMR acts as both a wave and a particle, which is our wave-particle duality. One other thing to note here that's really, really important, and we'll use it quite a bit later on here, is that this is the only formula so your answer can be in joules or electron volts. It's the only one. Because of Planck's constant here, where we have 6.63 times 10 to the negative 34 joules per joule second, or 4.14 times 10 to the negative 15 electron volt seconds. So that's really important that you remember this, because when we get further into the course, we'll see that others can't have that opportunity. Okay, so what is the energy of a photon? It has a frequency of 4.5 times 10 to the 14 hertz. Starting with what we know, we have frequency equals 4.5 times 10 to the 14 hertz. And so this here, we know that this is from the visible light. Visible light spectrum. Okay? Energy is equal to Planck's constant times frequency. So it's asking us what is the energy. It doesn't matter which one we choose. I'm going to use 6.63 simply because it comes first. And so we end up with 4.14 times 10 to the negative 15 electron volt seconds. And you're going to find these listed here in your constants on Planck's constant. So the first one listed is 6.63. So I arbitrarily always will default to that one. A beam of monochromic light, monochromic being of one color, having a wavelength of 580 nanometers, is incident on a detector. The beam delivers 910 electron volts of energy to the detector each second. Determine the number of photons incident on the detector each second. So our information that we have is 580 nanometers, energy equals 910 electron volts, Planck's constant. Because we're already starting out in electron volts, let's use this one. And then we can go on from there. Make sure that you're converting this so 580 times 10 to the negative 9 meters, or 5.80 times 10 to the negative 7, whichever one you want to work in. So when we want to find the number of photons, we're looking at this. And why am I choosing this one? Because that's what this formula is choosing. And so then we can go isolate for n is equal to energy times wavelength over Planck's constant times the speed of light. Can't believe that I just did that. That's a rookie mistake. Okay, we don't use x's at this level. N equals 424.9597 ... seconds to the negative 1. Therefore, based on sig figs, we can only have 3. 425 photons every second. Okay, and so you're going to want to work through these questions here that are listed at the bottom of the page.